This is Chemistry Podcast 9.6, and we're going to talk about how you can calculate pH of strong acids and strong bases, and also what acid-base ionization constants are. So the first thing you need to remember about a strong acid and a strong base is that strong acids are ionized 100% of the way. So if I were to, for example, put HCl into solution, I'm going to end up with H plus and Cl minus. None of this is going to be left together. It's going to completely break into the ions that make it up. So strong acids ionize completely. You don't have any of the compound left. You'll only have ions. This means that the concentration of the acid is equal to the concentration of the H plus. So for example, if this was 0.1 molar HCl, that means I also get 0.1 molar H plus, and I get 0.1 molar Cl minus, those ions. So because this thing breaks up completely for every one of these, we get 1 H plus and 1 Cl minus. So their molarities are the same as the molarity of the acid that went in. That means when we're doing these problems, it's actually a pretty easy problem because it says, what would be the pH of a 0.1 molar HCl solution? Well, just like I was doing in that example, if I have hydrochloric acid, it's going to split into H plus and Cl minus. And just like I said before, if this is 0.1 molar, that means that when this breaks up into the ions, I'm going to have 0.1 molar H plus, and I'm going to have 0.1 molar chloride ions. Well, I don't care about the chloride ions in terms of pH. What I care about for pH is the H plus, because we know that pH is equal to the negative log of the hydrogen ion concentration. So what I'm going to do to figure out the pH of the solution is I'm going to take the negative log of 0.1. And when I do that, I'm going to find the answer is 1. So the pH of my solution here is going to be 1. Our second problem here says, what would be the pH of a 0.050 molar nitric acid solution? So the first thing I'm going to do again is I'm going to write my nitric acid, and I'm going to show how it breaks up into the hydrogen ions and the nitrate anions. So that's what I've got. If my original molarity is 0.05 molar, then because this is a 1-to-1 for every one of these, I produce 1 H plus. The concentration stays the same. So 0.05 molar, 0.05 molar, and 0.05 molar. So there's none of this left. It's all been converted into the ions. And because I'm looking for pH, again, I'm going to look only at the H plus. I don't care about this one. That doesn't affect the pH. The H plus is what I care about. So in order to calculate the pH on this one, I take the negative log of 0.05, and we put that in your calculator and you get 1.30. So those are examples of how you calculate the pH of your strong acids. And remember, the strong acids are just the 6 that we talked about. There's no others. You can't do this for your weak acids because they don't ionize completely. So just like your strong acids ionize completely, so do your bases. Strong bases are ionized 100% of the way. And remember, your strong bases, you could recognize them because they have the hydroxide in them, and that's how you're going to pick them out. This means that the concentration of the base is equal to the concentration of the hydroxide ion most of the time. This does not work for strontium hydroxide, barium hydroxide, calcium hydroxide. Anywhere where you have this 2 right here, you can't do it. It will work, for example, if we think of sodium hydroxide. Sodium hydroxide splits into a +1 sodium ion and the negative hydroxide ion. Then the concentration is exactly equal. But here we have to do one more step that you need to just watch out for. So the first example, what would be the pH of a 0.1 molar sodium hydroxide solution? Just like I started the acid problems, I'm going to start by taking the sodium hydroxide and I'm going to split it into the ions that it forms. So sodium ions and hydroxide ions. 0.1 molar was my original concentration. So if this is 0.1 molar, because for every one of these we produce 1 sodium ion, this is also 0.1 molar. And my hydroxide ions are also 0.1 molar. In terms of pH, I want to know H plus, or I can work with the OH minus to get back to the pH. So sodium has no meaning to me. I don't care about it. The one I'm going to focus on in this case is going to be the hydroxide ion. The way I like to solve these is I like to find the pOH first and then subtract from 14. So remember, that's the negative log of the hydroxide ions. So I'm going to take the negative log of 0.1, and in that case it's going to get 1, which means that my pH is going to be 14 minus 1, which is going to be 13. If you stop and think about this, if you thought maybe that was the pH for a second, you need to remember that pHs that are lower than 7 mean an acidic solution. So when you got this 1 here, that couldn't have been the pH, that would have to be the pOH. So just watch out with your bases. You calculate the pOH first, and then you calculate the pH. So the pH of that solution would be 13. The second problem that we're going to do with these bases deals with calcium hydroxide. So again, I start with what I've got, which is the calcium hydroxide. This, when it breaks up into its ions, it's going to give me 1 calcium ion, and it's going to give me 2 of the hydroxide ions, because we have a 2 out here outside the parentheses. This originally was 0.1 molar, and because for every one of these we produce 1 calcium ion, the calcium is also 0.1 molar, but for every 1 mole of this, we produce 2 moles of the hydroxide. So that means I have to multiply the concentration by 2. So this becomes 0.2 molar. And that's what I'm going to deal with now to find my pOH and then find my pH. So my pOH is going to be equal to negative log of the 0.2 molar. And when I run that through the calculator, we end up with 0.70. And then to find the pH, you're going to subtract from 14. So 14 minus 0.70, and that's going to give you 13.3. That is the pH of this 0.1 molar calcium hydroxide solution. All right. Along with this, because those only dealt with strong acids and strong bases, we're going to talk ionization equations. And ionization equations mostly deal with your weak acids and your weak bases. That's really all we're going to use them for, and your weak bases. So we're not going to use this for our strong acids and our strong bases, just the weak ones. What you need to know about an ionization equation is that it shows how an acid or a base is going to react in water. How is it going to dissociate? What is it going to do? What are you going to get? General rules. Acids are going to give you, or acids, because of the Bronsted-Lowry definition, are givers of protons. They give away their hydrogens. So when an acid gives away its hydrogen, it's going to give it to a water molecule, and we're going to end up forming this hydronium ion, the H3O+. Bases like to take hydrogen ions. So the base is going to take the hydrogen from the water, and you're going to end up with the hydroxide anion. So acids give their hydrogens away, and you get hydronium. Bases take their hydrogens and they form hydroxide. General rules that you should know. So if we wanted to do an example here of what these would look like, we have hydrofluoric acid. What you do is you write hydrofluoric acid, and we always put plus water, because that's what these ionization equations show. How does this thing react in water? Because these are all weak, we're going to use double-sided arrows. These are not one-sided like our strong acids and strong bases. These are double-sided. There's an equilibrium going on. This is an acid. It's hydrofluoric acid. It's going to give its hydrogen away to the water. So we're going to end up with hydronium, and then what's going to be left over is just the fluoride ion all by itself. So this would be the ionization equation for hydrofluoric acid. The second one is ammonia, and ammonia is a base, but I'm still going to start it the same way. I put the ammonia with the water. It's a weak base, so I do a double-sided arrow. And in this case, because it's a base, it's going to pull a hydrogen from the water to itself. So it's going to form the ammonium ion, and then the water is going to be left as the hydroxide anion. So the hardest thing I think people struggle with is maybe the charge. Here, we're moving a hydrogen from here to here. And when we're moving a hydrogen, we're moving an H+. So the H plus goes to the water and makes it have a positive overall charge. Because the hydrogen has a positive charge and it's leaving this, the fluoride is left with a negative charge. The other thing you need to check to kind of make sure you did your charges right is that your charges here cancel out and equal the charge on this side. So over here I have a neutral charge of 0. Neither of these are charged molecules. On this side I have a +1 and I have a -1. Those will cancel out to 0, which is the same as this side, so I've done the charges right. Down here it's the same thing. We're moving a hydrogen ion from the water to the ammonia. So now the ammonia is going to become positively charged, and because it left the water, it becomes negatively charged. And I have a positive canceling out my negative, and this is neutral on this side as well, so the charges all cancel out. All right, along with your ionization equations, we're going to write what are called acid ionization constants. And your acid ionization constant, as well as your base ionization constant, is just an expression that shows how the concentration of the products are in relationship to the concentration of the reactants. So you put the products over the reactants. It's really important that since we're talking about only concentration, we're not going to include liquids like water. Water is a pure liquid, and we're not going to include solids. So the only thing that gets included in this are your aqueous compounds, because aqueous compounds will have a concentration. Liquids and solids don't, so they don't get included in this. And then the big thing about these and why scientists really like them is because we can tell how strong an acid or a base is, and we can compare it to other things. So the larger the Ka or the larger the Kb, the Ka is for the acid, the Kb is for a base. The larger these values are, the stronger the acid or the base is. And we'll talk about that as we do a couple examples with these. So Ka, the acid ionization constant, concentration of the products over the concentration of the reactants. What you want to do, and here's an example, is you want to write the acid or the base. You want to do it with water. So you want to write the ionization equation first. You want to show yourself this is what it's going to do with water. It makes writing this constant a whole lot easier. So I have my nitrous acid and I put it with water. Because it's an acid, it's going to give a hydrogen. So I'm going to be left with the nitrite ion, and we're going to form hydronium. So if I think about this, my acids are always aqueous. Water is a liquid, and your ions are always aqueous. So aqueous and aqueous. That means when I go to write my Ka right here, I am not going to include the liquid, which is water, and water will never be included. So water is never included when we write these. You include it to figure out what happens and what ions are formed with these acids or bases, but you're not going to put it in this expression, this Ka expression. Because we're talking concentration, we're going to use those square brackets again, just like we've used before. So what I do is I do the products over the reactants. So I'm going to look these two over that one by itself. We don't add them together, you multiply them together. So I do the nitrite ion and I multiply it by the hydronium ion. So even though we're adding them in the reaction, in the Ka expressions they get multiplied, and I'm going to divide it by the reactant, which the only one we include is the nitrous acid. So this is what my Ka expression looks like. You're not going to have to do any math or anything with these. You're just going to have to write them out and be able to tell that the larger the Ka is, the stronger the acid is going to be. So this is what we just talked about. Weaker acids have a smaller Ka value. Stronger acids are going to have a bigger Ka value. And if we think about that, if I wrote just a general equation here, Ha is just any weak acid you can think of. This is what we would end up with if we put it with water. Your products over your reactants is your Ka. And we know that the measure of the strength of an acid is how much it ionizes. So the more these acids ionize, the stronger they are, the greater your concentration of your products is. And the higher the concentration of the products, the bigger your value is going to be when you go to divide these. So the stronger your acid, the more products you have, and the bigger your Ka is going to be. This says write the ionization equation and acid ionization constant expression for hydrocyanic acid. So the first thing we always do, we're going to put it with water so that we can see what happens. My weak acids, double-sided arrow. I'm going to be left with the cyanide ion because the hydrogen here is going to go to the water. It's an acid, it's going to give it away. Whoops, that needs to be a 3. So this is my ionization equation right here. That's what I just did. Then it wants me to write the Ka. So for the Ka, I do the products. So that's going to be the Cn minus multiplied by the hydronium ion over HCN. Remember, we don't include water when we're writing our Kas. And that's all I have to do for this problem. There's no math, it's just writing expressions and equations. So just like there is an acid ionization constant, there's also going to be a base ionization constant, and we call that Kb. It's written exactly the same as Ka. You do products over reactants, don't include water, don't include solids. And the same rules still hold true. The greater your Ka is, or the greater your Kb is, the stronger your base is. So if your products are less than your reactants, your Kb is going to be smaller. For your strong bases, when it ionizes more, we have more products, so they're bigger than your reactants, and your Kb is going to be bigger. The example here says write the ionization equation and base ionization constant expression for the base methylamine. So the first thing I'm going to do is I'm going to take my base and I'm going to put it with water. Double-sided arrow. Because this is a base, it's going to take a hydrogen on. So it's going to become CH3NH3, and it will have a plus charge because it added an H+. And then my water will form the hydroxide anion. So this, again, ionization equation, just showing how it reacts with water. And then the second part of this is just to write your Kb expression. So for this one, it's going to be the CH3NH3+, and it's important that I include the charges, because these are ions, I need to include the charges down here, multiplied by my other product, which is the hydroxide ion, and I divide it by, not water, just the original methylamine, the CH3NH2. And that is it. So that's all I've got to do for those problems. Okay, that is the end of this podcast. You should be able to calculate the pH of strong acids and strong bases. And then you also need to be able to write weak acids and weak bases, how they react with water in those ionization equations, and also writing the Ka and the Kb expressions.